Hey, what's up guys? In the last video we looked into how we can solve the knapsack problem in a brute force and top-down approach, and in this video let's see how you can use the table filling approach to solve the knapsack problem in a much more faster way. Alright, now over here you can see the table that I have drawn here. Each table will represent all combinations of inputs. So if you look into the top-down solution that we did, in the top-down approach, all the inputs that are fixed except the capacity and the index of the item. So the whole input that varies for our function, solving function, is the index of the item and the capacity. So to represent all kinds of inputs for our bottom-up approach, we write a table like this. As you can see, in this table we are representing all the items along rows here and all the capacity, all the possible values of capacity from 0 till the given capacity, which is 12. So here I have written the value and weights of all the items, each of the items. So at the left, all the numbers 3, 4, 1, 2, 6 are the values, and these values at the right are the weights of the corresponding items. Okay, alright, now let's start with filling the values for our table. Now starting with the first row, which corresponds to 0 items. Okay, so here along the rows we are representing all the items that are included in our problem statement. So we are solving all the subproblems starting from the smallest subproblem. Okay, the smallest subproblem is one where there are no items given in the problem. Okay, so basically there are no items. 0 means no item. Now when we go to the first row, by then we would our problem would only have one item to consider, and we will solve the subproblem for all possible values of capacity. Similarly, when we go to the third row, there we will be including both the first item and the second item in the problem statement, and we will solve the problem for all the values of capacity and so on. So to get the solution to the given problem, we will consider all the given items, so in the fifth row, and the given value of the capacity, which is 12. Okay, for our problem statement, the total capacity of knapsack is 12. So the solution that we get is corresponding to this row for fifth item, the last item, and the capacity of 12. Okay, now starting with the first row where no items are considered. If there are no items, you can directly say that the value will be 0, because whatever the capacity of the bag, we are not considering any item, so all the values will be zeros. Okay, this is the first step that you need to take when you are solving any DB problem in a bottom-up approach. You first start by filling out all the cells corresponding to the smallest subproblem, that means the edge case or the base case. Okay, alright, now considering the first row, first column, which corresponds to a capacity of 0, when the knapsack capacity is 0, then whatever the amount of items that are given and whatever the value that is there, you cannot add any item into the knapsack, because the knapsack doesn't have any capacity to hold any item. Okay, so even here the solution, the maximum value that you can get out of it will be 0. Now the actual consideration of all the inputs in the problem statement begins. Okay, so moving to the first row, now we only have in this row, when we start filling from for inputs from 1 till 12, we only consider that our whole problem has only this item. Okay, item number 1 with a value of 3 and a weight of 2. Okay, so considering that this is the only item that we have in the problem, for a knapsack of capacity 1, we cannot include this item into the bag because its weight is 2. Okay, since we cannot include, the maximum maximum value is 0. Coming to the next subproblem, we have a bag with capacity 2, and if you look into this weight of this item, we see that we can actually include this in the bag. So the maximum value will be 3 because we can include this item. Similarly, for for a knapsack of capacity 3, we can include the item, so the maximum value is 3, and so on. For all these capacity which is greater than or equal to 2, we can easily include the only item. This is the only item we have considering this subproblem in this particular row, so all values will be 3. Okay, moving to the next row. In this row, we are considering all the problems which have both these items 1 and 2 considered. Okay, so here when we are filling the values, we consider that our problem has both these items. Okay, now for a capacity of 1, we'll see if we can add any of the items here. Okay, since both of them have weight more than 1, we cannot add, so the value will be 0. Now considering this capacity of 2, if we see, we can include only the item number 1 because its weight is 2. So the maximum value is 3. Coming to the next sub problem. Similarly, for a capacity of 3, we can only include the item 1. So maximum value is 3. Similarly, for a capacity of 4, we can either include item number 1 or item number 2, but because both of them will fit inside the knapsack with a capacity of 4, but we choose to include item number 2 because its value is more. Okay, maximum of 4 and 3. Now if you can observe the way in which we are filling the table, we can come up with a common formula, okay, common pattern directly by looking at the values as to how we can generalize this table filling algorithm. Okay, now let's take a closer look at how we actually concluded that 3 will be the maximum value. Okay, so here when you considered this sub problem with a capacity of 2, what we did was we checked if the capacity of the knapsack is greater than or equal to the weight of the item. Okay, since it was not possible to include this item inside, indicated by 4 being greater than 2, we chose that we cannot include this item. Okay, since we cannot include this item, when you exclude this item, you look at the previous row. Okay, you look at the previous row, which indicates the maximum value that you can get by excluding this item. Okay, item number 2. Okay, so we just copy the value of previous row, okay, which is nothing but the maximum value by excluding this item. So you can say, we can write a general formula. If at all your capacity of the knapsack is less than the weight of the current item that you are considering, or the current row that you are looking at, you can just directly copy the value. Okay, so copy the value in the previous row. Let's say this is the current row that we are looking. You can just copy the value from the previous row in the same column. Okay, current column. This will be the value of the maximum value for a given problem with these two items given, and a capacity for knapsack with a value of 2. Now similarly, when we move to the next problem, here also 3 is less than 4, so we need to exclude this item. By excluding the item, we just copy the value of the previous row, 3. Moving to the next sub problem with a knapsack capacity of 4, we see that you can include this item number 2 because its weight is less than or equal to capacity. So now you have two choices to make. Either you can include this item, but that means you are decreasing the capacity of knapsack by 4, okay, because 4 is the weight of the item. Or by excluding the item, you will get the extra capacity, you'll get the extra remaining capacity, but you will not be able to include the value that this item gives. Okay, so there is a choice to make, just like how you saw in the brute force approach. Consider that value which corresponds to the maximum value either by including or excluding. Okay, so maximum of, by excluding the item, what you do, you just consider the value from the previous row. Okay, because previous row is the sub problem where you did not have this item at all in the problem, so that means you are simply excluding this item, and you will consider the value in the same column, that is the current column. Okay, either that value which corresponds to excluding this item, or you include this item and add the value that this item gives to the value that corresponds to a decreased capacity of the bag. Okay, so how do you represent that in the table form? You add the value of the item. Okay, so the value of the current item and the maximum value that you have got till now by considering the decreased capacity. So what is the decreased capacity? The current capacity, which is nothing but 4 here in this problem, because we are considering this column. Okay, 4 minus the weight of the item, current item that we are considering. Here we write previous row because when you actually include the item, all that you need to consider is the maximum value that you can get by considering all the other items. Okay, so once you include the item, you include its value, add its value to the maximum value that corresponds to a problem where you consider all the other items. So that is why the previous row, which represents all the items till this row excluding this item, and corresponding to a capacity that is decreased now because you have included the item. Okay, so this is how you can interpret the table filling approach. So if we apply the same formula, what you can get is maximum of the previous row value, which is 3 here, this row, and the value of the item by including it with the previous row, that is row number 1, and a column which corresponds to decreased capacity. So 4 minus the weight of the item, which is 4. 4 minus 4 is 0. So table of 1 of 0. Table of 1 is this, 0th index is this. This is 0. Okay, so T of 1 of 0 is 0. That just means that by including this item, you are decreasing the capacity of the bag, and by decreasing the capacity of the bag, whatever the value that you can, maximum value that you can get out of it will be 0. Okay, because the remaining capacity is 0. So 4 plus 0 is 0, maximum is 4. So we will just write the evaluated value of this expression. Similarly, for a capacity of 5, since 5 is greater than 4, you can actually either include or exclude this item, and you will apply the same formula, which is maximum of, by excluding you get 3, by including you get the sum of value of this item along with the current maximum value by considering all the other items. Okay, so the previous row, which is 2 minus 1, and 5 minus capacity is 5 minus the weight of the item, which is 4. So that is T of 1 of 1. T of 1 of 1 is 0, so 4 plus 0 is 4. Similarly, the maximum value that you can get is 4. And if at all you could not arrive at this formula directly, I suggest you go on solving some more subproblems like this, some more subproblems of the table by yourself without applying any formula. You can, because the whole problem would contain only 2 items, you can easily guess the maximum value. You can easily consider what is the maximum value for that particular capacity. Okay, so that is how you go on filling the table, and at some point of time you will get to see the pattern that is emerging, and you can come up with a formula like this, generalized formula, very easily. Okay, so let's continue with the same approach. For a knapsack capacity of 6, you see that you can include this item. So you can actually see that you can include both the items without exceeding the capacity. So the total value, maximum value would be 7. Okay, so let's calculate that using the formula that we got. Okay, since capacity is 6, we can either exclude that item. By excluding the item, we just copy the whatever the value that is there in the previous row, which is 3. Either we exclude the item or we include the item. By including the item, we add its value. Okay, 4 plus, add the value of the current item and the maximum value that we have got by considering all the other items. Okay, so previous row, that means we are considering all the other items other than the current item that we are looking at. Okay, previous row is T of 1, and 6 minus 6 is the total capacity for the problem that we are considering. 6 minus the weight of the item. Okay, what is the weight of the item? That is 4. 6 minus 4 is 2. Now T of 1 of 2 is 3, so we add T of 1 of 2 is 3. So maximum value is 7. Okay, 4 plus 3 is 7. This turns out to be 7. Now you can write 7. Let's say I choose some random row, this cell. Now this cell represents a subproblem where the problem consists of these 4 items. Okay, these 4 items, and the capacity of the knapsack is 9. All we are doing is we are going on solving all the subproblems starting from the smallest one, that is corresponds to the base condition, and by go on solving all the subproblems one by one, we can come up with a generalized formula like this, which applies to all the cells, and we can use the same. Alright, now talking about the capacity of 7, you can easily guess that all the other higher capacity problem will naturally contain 7 as the maximum value, because we can include all the items that are given in the problem. Now moving to the next row, this row corresponds to the subproblem where you are given with only these 3 items. Okay, so these 3 items, item 1, 2 and 3 are the only items that you are considering, and we go on solving all the subproblems starting from the problem where knapsack capacity is 1. Now we can directly see the capacity is 1, which is less than any of the items weights, so the value will be 0. Okay, so that means when value of capacity is less than the current item's weight, you will just copy the value from the previous row, because previous row contains the maximum value that you can get by excluding this item. Okay, because this item was not even there in that row when we are considering that subproblem. Okay, so moving on to the next subproblem, capacity is 2. 2 is less than 3, so we can't include this item. So the only option we have is by excluding the item number 3. So we just copy the value from the previous row, which is 3. Coming to capacity of 3, we can see that we can either include this item or exclude. Maximum of 3, that which is got by excluding this item, or we include the item and consider its value. Okay, so maximum of 3, and by including we add its value and consider the previous row is 2. Consider all the other items and get the corresponding maximum value by decreasing the capacity. Okay, so the current capacity we are considering is 3 minus the weight of the item, which is 3. 3 minus 3 is 0. T of 2 of 0 is 0. Okay, so 1 plus 0 is 0, maximum is 3. For a capacity of 6, we can include item 2 and item 3, item 2 and item 1 with a value of 7. So we can say maximum of one choice by excluding the current item, or by including the item we consider the table value corresponding to second row, and 6 minus 3, which is t of 2 of 3, which is 3. So 1 plus 3 is 4, maximum is 7, so on. Similarly, you get the same value of 7 for all these weights. Now when the weight, when the capacity of the knapsack is 9, you can see that you can include all the items, item 1, 2 and 3, because total weight would be 9. Okay, so by including all of them, you can directly add the value, which will turn out to be 8. Alright, once you fill the table using the formula, we'll get the values like this. Now let's fill the value for the last 3 cells. Okay, for a knapsack of capacity 10, considering all the items that are given in the problem, the maximum value would be, since capacity is 10, we can either include or exclude, so it would be maximum of 8 and 6 plus the table value corresponding to previous row, that is the 4th row, and the decreased capacity, which is 10 minus 5. 5 is the weight of the 5th item, item 5. So 10 minus 5 is 5. T of 4 of 5 is 4, so 6 plus 4 is 10. For a knapsack of capacity 11, the maximum value would be 6 plus table of 4 of 11 minus 5. 11 minus 5 is 6, that would be 7. So 6 plus 7 would be 13. For the last cell, you can see that we are considering a knapsack capacity 12, which is the actual problem statement, and we are considering all the 5 items. So the value of last cell would be maximum of the value that we get by excluding the item, which is nothing but the previous row, that is 9, and the value by including the item. By including, we get a value of 6 plus t of 4 of 12 minus 5. 5 is the weight of the item, that would be 12 minus 5 is 7. Okay, so 4 of 7 would be, again 6 plus 7 is 13. Okay, so this is the maximum value that we can get by considering all the items that are given for a knapsack of capacity 12. Okay, so this is the solution to the problem, but this is not the complete solution. The complete solution involves printing the items that are actually included in the knapsack. Okay, so before we do that, first let's code the solution for finding the maximum value using the top-down approach like this. Okay, so here we have the brute force approach for knapsack problem. Now let's write the bottom-up approach. The bottom-up approach only takes the weight vector, the weight array and the values of the items, and the capacity as input, initial capacity C. Its output would be the maximum value that we get by considering all the items. So we start by having a table, okay, which is nothing but a 2-dimensional array. Here we'll fill the table such that we will consider all the possible combinations of the inputs, okay, all the possible combinations of the sub problems. Okay, so I from I is equal to 0 till I becomes equal to the total number of items. Okay, so that is n. On the other dimension, we consider all possible values of capacity, because those two are the only varying quantities. J is equal to 0, j less than or equal to the given initial capacity, j plus plus. Okay, so the initial condition, whenever my I or j is 0, as you can observe here in this problem, if either j or I is 0, we know that we cannot include any item, and that's why the value is 0. So table value will be 0. In all the other cases, we'll just check 2 more cases. One case is the current item that we are looking at, its weight is actually greater than the capacity of the bag. Okay, so greater than the remaining capacity. The capacity is represented by this variable j, and the weight of the current item I is greater than the current capacity j, then the only choice we have is to exclude the item. My maximum value will be the same value that I copy from the previous row. Otherwise, what we do is, this means my weight is less than or equal to the current capacity of the bag. So we just consider two choices. One is by including the item and the other is excluding the item. Whatever is the maximum, we'll just take that. Okay, so the value for this particular cell is maximum of either by exclude the item, which is nothing but table of I minus 1 of j. By excluding the item, we will not add the value of the current item. other choice is we include the item. By including the item, we add the value of the current item, and we take the maximum value corresponding to the decreased capacity. Okay, so J is the initial capacity of the bag, J minus the weight of the current item by including that item. Okay, so this will be how we will fill the table. Now, what is the actual solution? The actual solution to the given problem lies at the last row and last column of this table. That just means the nth row and the cth column. Okay, so we just return the value present in nth row and cth column. Okay, so this will be the solution. Now if we call our function with the necessary inputs, that is weight, values, number of items, and the total initial capacity, let's execute it. You can see that it gives a value of 13. Okay, so this is the conventional standard approach of solving a DP problem, and it's quite efficient because it does not involve any recursive calls. We are taking a iterative approach by solving all the subproblems for this table. Okay, so this is the one part of the solution where we get the maximum value that we can get, but the actual problem is to find out the items that you have actually included in the knapsack. Okay, so to do that, we'll follow this procedure. Okay, we'll start by looking at the last cell, that is the last row and last column cell, and see if the value of this cell is same as the value of previous row. If the value of this cell is same as the value of previous row, that just means we have excluded this item. Okay, item 5 we have excluded if the value is same, because only when we have excluded this item the value can remain same. Otherwise, by including the item, the value would have got increased. Okay, so since here we can see that 13 is not equal to 9, that just means we have included this item 5. So we can say that we have included item 5. Okay, so now by including item 5, what you did is you decreased the capacity of the bag from 12 to 12 minus 5. What is 12 minus 5? 12 minus 5 is 7. Okay, so you directly go to the 7th column now and just see if this particular cell has the same value as the previous row. Okay, now we have included the 5th item, so by including it, our capacity has decreased to 7. Now all we need to look at are the cells from this particular cell till this cell. Okay, till 0. Alright, now here we can see that 7 is equal to 7. That just means we have excluded the item number 4. So by excluding the item, we just move to the previous row. Okay, our business with this particular row is over and we move to the previous row. Here also you can see that 7 is equal to the previous row. Since both rows have the same value, that just means we have not included this item 2. Okay, so item 3 is excluded. That's why we conclude the item 3 is excluded and move to the previous row. Okay, now we only have to deal with the cells from this cell to this cell, 0th row and 0th column. Okay, so here you can see that 7 is not equal to 3, it's previous row. That just means we have included item number 2. Okay, so item number 2 is included, item 5 and 2 are included. By including item number 2, we effectively decrease the capacity of knapsack from 7 to 7 minus 4. 4 is the weight of this item. Okay, 7 minus 4 is 3. So you move to this cell corresponding to capacity of 3. Okay, because that's all the capacity that is left in the bag. Okay, here you can again see 3 and 0 are not equal. That just means we have included item number 1. Okay, so we included item number 1. By including, we decrease the capacity from 3 to 3 minus 2. 3 minus 2 is 1. So we reach here. Here the value of the cell is 0. That means the maximum value at that point is 0 itself, so there are no more items that are added. So this is the solution that we get. Items 5, 2 and 1 are included. How do we code the solution? Let's try to code that solution. Okay, the solution of finding the actual items that are included. Let's write a function find included, which takes the table as input and the total number of items and the capacity C. So we continue applying the method until the value of the table becomes 0. Okay, table of n of C becomes 0. We continue this. Initially my I will be equal to n and capacity will be equal to initial capacity Okay, and we continue until the value is not equal to 0, till the value is not equal to 0. Okay, here we check if the value of table is equal to the previous row. Okay, if it's equal to previous row, we just exclude the item. Okay, how do we exclude? We just go to the previous row, I minus minus. Otherwise, we know that the values are not equal, so we include the item. So by including the item, let's just print that item I is included. Or I can also write this as when the value is not equal, we just include the item. Okay, and by including the item, we decrease the capacity by the weight of the item. Okay, so W of weight of the item. So we also need to take the weight of the item as input. Okay, so we decrease the capacity by the weight and we move on to the previous row. Okay, so if at all my table values of the current row and the previous row are equal, we will not be including that item. We'll just move on to the previous row. That just means we have excluded that item. If at all the values are not equal, then that means we have included the item. We print the inclusion and we decrease the capacity. Okay, so we continue this until the table's value will be 0. Okay, so let's call that function find included. We'll send the table and the weight and n and the initial capacity c. Alright, I have just returned the function above this function. Now when we are printing the included items, instead of printing the index, we can also print the number of the item. That just corresponds to the conventions that we have followed here. Okay, so now if I execute this, you can see the same set of items are included. Item 1, 2 and 5. Here also in the solution you can see item 1, 2 and 5 are included, which corresponds to a total weight of 11. If you want, you can also find the weight here, okay, by keeping one more variable. Okay, this is how you use the bottom-up approach to find a solution to the given one DP problem. And this kind of pattern, if you understood this clearly, then you'll be easily able to solve a lot of similar DP problems. And by understanding this pattern, it becomes very easy to come up with a generalized table filling formula like this by starting with a top-down solution first, by starting with the brute force solution first. So this is what we will be doing in future for all the other DP problems that we'll be solving. So we'll be starting out with a brute force solution and optimizing it using a bottom-up approach. Okay. Alright, hope you guys found this video useful. If you did, please like and don't forget to subscribe. See you guys next time.